Okay,
Hi.
I can see people starting to filter in now, so I'll make some very brief beginning of session announcements. My name is Scott Collis. I'm from Argonne National Laboratory. Myself and Kristen Thung are the co-chairs for the Earth, Ocean, Geo and Atmospheric Sciences mini symposium as part of SciPy 2021. And just before we get going, I want to add my thanks to all the organizers for the conference, but especially to our reviewers. We had an army of reviewers that reviewed and scored every proposal. This year went particularly smoothly. We had at least 4 reviewers per presentation, and really it made Kristen and my job very, very easy when it came to curating these wonderful talks you will be seeing today. So without any further ado, I would like to introduce, and I do apologize for my mispronunciation, Bowdoin Raoult from European Center for Medium Range Weather Forecasts. Bowdoin.
Okay, thank you very much, Scott. So my name is Baudouin, and I work for the ECMWF. So just that to introduce my organization, it's an international organization that is composed of more than 30 countries, which actually do medium range weather forecasts. So we are actually producing forecasts every day, and we have a very, very large archive in the order of 300 petabytes of data, and as many people, we are starting to really invest into machine learning. So my talk is about a package we are developing here. It's still in sort of alpha stage. So what we did is to look at the way people work and look at some Jupyter notebooks. And what we saw was a lot of code, which is for data wrangling, to access the data, wget, curl, try to retry to loop, and then unzip and tar, try to extract the data. And then usually the data is not exactly as you want it. So in weather forecast, it's very often in GRIB, which is a WMO standard. It could be NetCDF, we have CSV and so on. And then you do your machine learning, and then the rest is about trying to plot the results into some sort of nice map. And usually you also have a lot of code there to project properly, to choose the right colors and so on. And the number of lines of actual AI and ML is quite small. So we started this project, which is to aim at really simplifying the access to the data and let people focus on science. This is a sort of example, a sort of goal we want to do, where you will simply load the data set by name, give a few things like the domain and the period, and then plot a map. This is an actual example, 3 lines of code, and you have a map of 2-meter temperature, in this case, over France for this given time of the date. Now, another example as well, this is the hurricane database from NOAA. Again, this is a sample data set. You load the data set by name, and you select the basin, that Atlantic basin, and then you select a tropical cyclone, and then you just plot it. So the idea is that we can plot something and choose the right plotting attributes based on the data itself. So why Python? I mean, it's the wrong community to explain, but I have that slide because I showed this presentation to many other groups. Of course, you know everything here. First, it's a great community software. You have NumPy, you have Pandas, you have Matplotlib, and so on. You have lots of tools in machine learning. And also in our community, which is ocean and atmosphere, you have NetCDF, XRA, CFGRIB, which I understand is also used elsewhere. And ECMWF has been also wrapping some of its own packages to decode the WMO formats into Python, as well as our plotting package called Magix. And we provide APIs to our data sets in Python. So Python was the natural choice for this package. Sorry, I went back here. So where do we see? So where do we see this? So there is an ecosystem, as you know, and we see ourselves really between the sort of specialist data formats like grid buffer and the data sources, like getting data from an HTTP site or from an object store, from an API, and then transforming this data into X-array, pandas, NumPy. We don't try to redesign the wheel. We really want to be where our expertise lies, which is actually managing meteorological and climate data. So the first target is really for Jupyter notebooks, and the code should run anywhere. And we want to minimize the boilerplate code and provide seamless access to data and plotting. Be completely interoperable with all the packages that have been presented this week, and so that people can focus on science. So a data set is an abstraction, which this is not a new concept. You have packages like Intake that and even Google data sets, they offer the same principle. So a data set has a home page, has a license. It's something you can name. And the way we want to implement interoperability is really that we load the data set by name, and then we have all sorts of converter functions, so 2X-array, 2 pandas, 2 NumPy. And for example, if you want to do machine learning, you could load the data into a training set and a test set, and that should be the maximum piece of code that you should have to do. And we also want the plot, because that's also part of our expertise, to be done as seamlessly as possible, and with the understanding that the data itself knows how best to be plotted. So a tropical cyclone track knows that you plot it as a track, and a field of mean sea level pressure knows you need to plot it as isolines, and the temperature as a shading color. And the way we want to do interoperability is really to borrow from NumPy, Pandas, Keras, all those names which are familiar. So in the first example at the top, you would see if you use the Keras dataset MNIST, you will have something like load data, and that returns you 2 pairs of tuple. So in the same way, we want to have the same sort of signature to our data set. So you can really plug in a climate or meteorological data set into an existing TensorFlow program. So I have a small example here, something I did a long time ago, very, very trivial example. So just the first step is to import packages. So we import TensorFlow and ClimateLab. And then we have a trivial data set called HILO, which simply contains a collection of fields of geopotential 500 hectopascal, and they are labeled being a trough, a ridge, a high or low. So these are the example of some of the training set. And then you will do exactly like you would do in Keras. You will load the data set, you explain how you want to split between test and trace, and train and test. Then you create your model, then you compile it, and you train it. And it does work quite well. You see an output here where you can predict a few fields, and they're different, high, low, trough, low, and ridge. And if you put everything together, you see that 99% of the code is actually the code using Keras and TensorFlow. The rest is really minimum to access the data. So that's the aim. It's a hard goal, and we are starting, but that's the aim. So you did not see any code for data retrieval. You did not see any code for decoding of the data or converting the data to NumPy. It's all done for you. So the concepts behind are the following. First, we have the data set. The data set is anything that you can name, site, a home page, and so on. The data source is more an access method. So an API, so we have an API to our data, or a URL, or database endpoint, that's a source. And then we have one which is called a reader, which will try to make sense of a file. Because usually when you download a file via an API or URL, then you need to actually decode it. So CSV, netcdf, nothing new here. We did not try to code anything new, just direct the code to the right package. So if it's a CSV file, it will go to Panda. If it's an SCDF file, it will go to Xarray. And then we have two other classes called filtering and merging, but this is work in progress. We still have to do a lot. It's to be able to combine the CSV files and filter collection of files into a single one, again, using existing tools. So every object, whether they are a data source or a data set or a reader, are supposed to implement a 2 NumPy, a 2 Xarray, 2 Pandas, 2 TensorFlow dataset, and so on, and the plotting. So there are a lot more. It's just to illustrate, with the understanding that they know best how to plot, how to convert. So a dataset will know how to be plotted, the source now how to be converted. So this is a kind of we use delegation. So a data set will delegate to a source, which will delegate to a reader. Now, if the data set class can implement the converter, that's where it should be. If it does not implement the converter, this is delegated to the source, which delegates to the reader. So, for example, we have a grid reader that reads grid format, and it can go from grid to Xarray using the CFGRIB package. But if you prefer that your data set does a different conversion, you can implement it there. So this is just to illustrate in terms of code how it's working. You have my data set to Xarray, and you may even, the code can finish into my data set .source.reader.xarray. All those intermediate members are not supposed to be public, but this is just the sort of architecture we have inside. And in the case of plotting, for example, we have a data set for a competition of machine learning on seasonal and sub-seasonal forecasting called S2S. And for example, you can see here that if the data set decides that the map should use red contours, this information will go through the classes, and the netcdf, for example, if it's a netcdf file, will know that it's a field, therefore it should be plotted with isolines, and the bounding box, or the geographical bounding box is whatever it is here. And then at the end, you have a sort of a communication between various actors in the code to decide how to best plot this sort of data. So if I come back to that slide, usually what you have, of course, we don't implement everything. So you have gridded data, so grid, grib, netcdf, zar, which usually can return NumPy or Xarray. And you have point data like CSV or buffer, which is WMO for observation, that can return a to Panda or a TensorFlow dataset. And all of them can be plotted. So again, if you plot one of the top, you will get this sort of map at, and if you plot one of the bottom, you've got that map at the below, which is a tropical cyclone track. I don't remember exactly which cyclone is that. Okay, and usually an example. So again, just to show, you can load a file directly. The source can be a file, the source can be a URL, the source can be ZAR, and then you just load a source, give it some parameters, in this case a file name, and then get the 2x array. And this is with a grib file, and you will see, and you can plot by iterating all elements of the source. And you can see here, you don't see any graphical attribute because they are selected automatically for you. temperature is a shading from blue to red, and mean sea level pressure is other lines. And the same with NetCDF, and you will not see the difference here. It's a NetCDF that contains the same information, but you use it exactly the same way, and you have the same plot, but starting from NetCDF. So now this is really proof of concept. Our aim is really to support AI machine learning reference data set when they exist. So it's not to cover every data set, but the aim is really machine learning. There is a data set already called the Weather Bench with the reference here. Météo France has put together also a data set called MeteoNet. We have this competition I mentioned earlier that started not so long ago to use machine learning on subseasonal forecasts. And then we did as a proof of concept access the Earth date from NOAA and so on. But the aim is really machine learning data sets here. Sources, currently we can read local files with a pattern if needed. So you can have something with a date in it and say all those files that match that pattern. And the same with URL. So HTTP, FTP. And we have our two APIs, and we are working now on ZAR. So anything that ZAR can do, we can read. It's in development, so directory, zip file, S3FS. We implement caching because when you download a file and usually you unpack it because it's a zip or a tar file, we cache it into the user's workstation. So this is not too bad. It's working well. We use an LRU, so the less old data is evicted from the cache. And we try also to follow, if it's a URL, the caching method from HTTP. So caching here in the user's workstation is really for Jupyter notebooks. So if you have a notebook, the first line would be download this data set and then do some data analysis. If you work like I do in a notebook, you rerun your notebook over and over again from the beginning. So you don't want to re-download. So caching was really the first thing that went in. So you only download once. Mirroring is something we are looking at. The idea is that an organization may want to organize a wide organization-wide shared cache. So that's an idea to be developed. But if you have a favorite data set that is not from your organization, but a lot of researchers use it, I think we should be able to have a mirror there. Now, and the last source we have implemented is what we call a multi-source. So imagine it's a collection of sources where you can combine them virtually. So you have a collection of NetCDF, but you can have a collection of ZAR, a collection of CSV, and the idea is to show them as a single source. So sometimes it's trivial, like for example, two pandas from the multi-source is simply to use pandas concat on all the sources. Iterate, it's just to chain all the sources, but there are things which are more complicated to merge. Xarray has many methods to merge Xarray data sets. If they are different, it's very hard. So we are also looking into that. Readers, so we can read NetCDF again because we use Xarray, we use NetCDF Grib, NumPy arrays, and CSV via pandas or TensorFlow has a way to read CSV as well. BUFR, which is the WMO standard for observation, ODB, which is a bespoke format for observation at the SMWF, and also all sort of multi-file collections. So the directory is a collection of files, and the tar file and the zip file are collections of files as well. So this is what we have. And what was very important for me is that in the title of this talk, we say a framework. We want people to write plugins. Again, this is not invented here. We looked at a package like Intake that does it very well, and I think Xarray is also having this notion of engine, which is a plugin system in a way. And the idea is that you can write a new source or you can write a new data set as a different package, which allows us to have them developed, tested, published independently as well, even have a different license as if you want. And then when a user does pip install and some of a new data set, it will be available to ClimateLab to the end user. So currently we do a plugin for data sources and data sets, but we could we consider developing it for more readers, which is support more data format and so on. My role is really to work on the framework part, so that everybody can develop their own new plotting style, and even we use Magix to plot. But if you want to plot with another plotting package for maps, we should be able to do it. It may not be that straightforward, but that's the plan. Now, the next steps, so as I mentioned before, work on caching and mirroring. These are very important aspects of the problem. And filtering and merging of data sources together. It's a hard problem. Lazy loading of data, that would be very important. Again, we don't want to do anything here. We want to rely on Dask. We want to rely on TensorFlow doing it for us, but just learn how it's working and add it to the package. An interesting one, this is a bit of a pet project of mine, is the unified vocabulary. If you look at several data sets, sometimes something will be called temperature or T or 2T or temp or something. If you look at even X-ray, you will see lat and long and latitude, longitude, all sorts of. So for the end user point of view, having to change vocabulary from data set to data set is not very friendly. So it would be nice if we could have a sort of automatic translation between a unified vocabulary and the data set native vocabulary. This is a big, I know lots of people have been working for 20 years on that, so it's not a straightforward thing to do, but at least if we will stick to the CF convention as a vocabulary, for example, which happens to exist, that will be a good starting point. And seamless integration between data set, that's something I wanted to do, and I have an illustration here. So imagine here, I get Katrina, which is, I think you all know in the US, which in 2005, and then so I get the track as a pandas frame of Katrina from the hurricane database, and then I want to retrieve the geopotential at 500 hectopascal from ECMWF reanalysis ERA 5. And here, what we just do here is to pass the panda frame to the retrieval from the CDS. And what ClimateLab does is that it knows that the date has to be a time, and therefore extract from the pandas frame the date and time. And area is a geographical representation, so extract from the panda frame the bounding box. And then you plot. And the plot you see on the side is exactly the output of that. So I did not need, as a user, to extract the time, to extract the bounding box and pass it to the next plugin. I want them to talk to each other. Okay. So here, any pandas frame that has a time dimension and a lat and long, you could pass to a plugin that requires a time dimension and a lat and long for the next step. Again, this is, for me, exploratory, but it does work, at least this sort of example here. And interactive maps. This is a lot more difficult because we need the support of Jupyter notebooks, but we could have, in this case, a WMS, so this is leaflet showing a tropical cyclone map in the same way. This is super experimental, and it works on only, I think, on Jupyter notebooks, doesn't work on Jupyter Labs. but I think eventually we can get there. And again, I want to stress we want to be fully interoperable with Pangeo, Stack, so Intake, ZAR, Dask, and with the aim as focusing to machine learning ready data that can be used as seamlessly as possible in Keras, TensorFlow, PyTorch. And we need to work on documentation as yes. And that's it. So it's alpha. You can install it. It has been tested on Mac, Linux, Windows. We have doc, which is not very up to date, but we try, and we are happy to have some feedback. And that's it. Thank you.
Thank you, Baudouin. You're perfectly on time. Fantastic. Yes. I'll start with a very simple question first. Amor wants to know, can you share these slides with us? And I'll just quickly add one answer to that. And all these talks will be available. The recordings will be on YouTube sometime after the conference is finished. But Baudouin?
Yes, yes, we can share the slides, yes.
Perfect. Another question for you. What does it mean to target Jupyter notebooks? Can you use your code within a regular Python application?
Yes, you can. But it's not the same writing some sort of batch. This is, for me, I really wanted to do something that can be used in a Jupyter notebook. So the caching, for example, if you run a batch job that does number crunching in Python, you would not use caching. You will work differently. You will download the data and then do. Okay, so it's really interactive work.
Someone who always has to comment out the load line in my Jupyter notebook, so I'm not constantly reloading. I really resonate with your point there. I have another one here. Oh, someone wants to know just basically what's the kind of resolutions of the weather data sets you deal with in this application in ECMWF?
Well, anything. I mean, ECMWF, for example, our model currently is a 9-kilometer grid. So global. So that's the resolution. So I don't know. A single field is a few megabytes. Now, that being said, it works for 1, 2 fields and so on. We aim at trying to let people, go through 10 years of data.
Yeah.
But again, relying on Dask, relying on.
And I don't know if you're on the Slack workspace for the conference, Baudouin, but you might want to put the link to the slides or something in there like that, or on one of the birds of a feather or something like that later on there. Just a request from the chat to include a link sometime. Kristen points out that check out CF X-ray for generic referencing of axes and coordinates. And a question from Martin Yeo. Have you looked at the Iris package while writing this? And maybe just
yes.
How do you think they will interact, Iris and this?
Yes. We know very much of Iris because that was developed by the Met Office. And I think even Iris existed even before X-ray. Okay, but in our case, it was really to focus on a very narrow bound, which is decoding of data into NumPy. So I think Iris does a lot more.
Maybe I can expand on that question a bit. How do you see ClimateLab interacting with MetPy as MetPy adds new calculations, so equivalent potential temperature or something like that? Are you going to bring in something like MetPy as a dependency, or do you expect them to be fairly independent packages?
No, I think for me, again, it's really focus on bringing the data set in the user space, and then you can call anything. You can call any. So I'm not very. I know of MetPy. I'm not familiar with, but I guess you can pass your NumPy array to MetPy. So the plan now is not to put any number crunching in ClimateLab. Nothing. No interpolation. No. All the computation exists within other packages.
And just one final question. I've only got time for a little bit more, which is from Maria, who asks, is it possible to do vertical cross sections of three-dimensional
So again,
data?
this is why I don't think that's the role. The role is to bring it into a form so that you can call a package that does a cross section.
Yeah. Okay, that's actually really cool. And we had this kind of talked a little bit about in some previous talks as well, having anti-features, knowing what the clear role of your software, which makes it maintainable, is super important. So thank you again, and thank you everyone for all the questions, and I'll see everyone back here in 5 more minutes for our next presentation.
Thank you.